We now turn our attention to structure formation in the universe. Actually, since the original disappointment at the failure of classical cosmological tests due to galaxy evolution in 1970s, until the revival of precision cosmology in late 1990s, this was the main subject of cosmological research. So here is the problem in the nutshell. We see the density fluctuations in the early universe imprinted on the cosmic microwave background photosphere. There are roughly parts in a million. Today, we see large-scale structure, clusters, filaments, voids, with density contrast of about 100. And then, within them, there are galaxies whose average density, within, say, half-light radius, is about a million times larger than the surrounding density. So how do we go from fluctuations that are a part in a million to large-scale structure that is factor of 100 over dense to galaxies that are factor of million over dense? And that is the problem. So we believe that the original fluctuations came from quantum fluctuations in the early universe, due to fluctuations in number of density of particles, and then they're inflated through the inflationary era to the large-scale structures, or rather seeds of large-scale structures. The matter then falls into them, and the density contrast grows. So the observed thing is fluctuations in microwave background, because the radiation and baryons are coupled before the recombination, which are parts in a million. But we also observe galaxy-like structures at the redshifts greater than 6. Those are luminous quasars and even some real galaxies. And so we know that at least some little pockets of the universe have achieved the density contrasts, which are not a part in a million, but a million, 12 orders of magnitude. And the time elapsed from the microwave background release until then is of the order of 500 million years. So this is not an easy thing to achieve. And the question then is, how do we go from such small seeds of density fluctuations to the large density contrast that is observed in the objects that we see? Well, here is a schematic flowchart of what has to happen. It begins with inflationary physics, or very early universe physics, which is not directly observable except as consequences of inflation. But then those fluctuations will grow, and we see their imprint in microwave background. Even after microwave background is released, they do grow through gravitational instability. The dense spots will attract more matter, become denser. That part is fairly easily understood and even modeled. It's Newtonian gravity because it's a weak field. But then gas falls into those potential wells, gets condensed, it dissipates energy as it falls in, it makes stars, stars dump energy back, and those are very messy processes which have to be modeled hydrodynamically through radiative transfer. So there is transition from relatively simple, elegant, theoretical treatment of more or less geometry and gravitation into the really messy hydrodynamics, radiation physics of what actually happens to the baryons after the recombination. So let us set the stage for this. In the early universe, we know that it's very close to the critical matter-dominated universe, matter radiation, and so it's a very simple overall Friedmann equation, regardless of what the universe will evolve to later. Early on, it's really close to omega matter equal 1. But then let's look at an overdense region, somewhere inside that exactly critical universe. It is essentially like a little closed universe of its own. And initially, of course, it expands, but as you know, since its density is greater than critical, and surrounding universe is at critical, so overdense one must be, that means that at some point, you'll have to turn around and fall back upon itself. So let's just subtract those two equations, and so that's Friedmann equation for the difference in density, which we can simply rewrite as follows. So that's the difference of densities, but really we're looking at the density contrast, so let's just divide it by the mean density, and so we'll call that as an overdensity, a little delta, and its equation is shown here. Now, since the density is inversely proportional to the scale factor, this is density of the matter, remember, so it just gets diluted as the cube of the radius. We see that the density contrast, the delta, will grow as the first power of the expansion factor R of t. And we call that the era of the linear growth of perturbations. So between any two different redshifts, the change in the contrast will be given by the ratio of 1 plus redshift, or rather inverse thereof. So let's try this for microwave background, roughly redshift 1000, to say first quasars roughly at redshift 5 or so. And we find out that the density contrast should have grown by a couple parts in 1000, whereas it should have been a million. So we're off by 9 orders of magnitude, and clearly linear treatment does not apply. The solution to this is in part that at the time of the microwave background, the fluctuations that we see are those in baryons and photons, but underlying them are much deeper fluctuations in dark matter. And those have been growing since the universe became matter dominated. So this is another reason why we think the dark matter must exist, because without it, we would simply not obtain the large-scale structure that we see. And that's a key idea, that density fluctuations are dominated by the dark matter, which, as you recall, is several times more by density than regular baryons. And those fluctuations grow even before the microwave background is released. So the fluctuations we see in microwave background are just a little icing on the cake. And after that, those baryons can fall into those already pre-existing potential wells built by the dark matter. Next time, we will address this process in a little more detail.